Good day, everyone. So we're going to be creating an LED sequence using the I/O ports of a microcontroller. So in the next picture, you will see a typical schematic diagram of a microcontroller circuit. So for our circuit components, we will utilize Proteus and then select these components for us to connect our microcontroller circuit. So first is a 5-volt power supply circuit, a crystal oscillator, PIC16F877A microcontroller, 16 pieces of 220 ohms, and LED, 110 kilo ohm resistor, and lastly, a normally open push button for our max master. So for the procedure of our circuit setup, we will connect the basic components of a microcontroller, which we already done in activity number 3, and then connect all the resistors and LEDs at port B and port C. So for our objective, we need to create at least 3 LED sequence patterns, and then we need to connect LEDs at port B and port C. So these connections for the LED was already done, and then it was accomplished in the last activity. So let's start. So in programming, we need to utilize 2 software. First is the MPLAB XIDE, which is our integrated development environment for our assembly language programming. And then next one is the Proteus. Proteus is a circuit designer software that can also function as our simulator of microcontroller chips. So we're going to open MPLAB XIDE. So you will be seeing the start page of the MPLAB. So on your upper left, you need to click File, New Project, and then under the Microchip Embedded category, you will select Standalone Project. Click Next. On the family, you will select mid-range 8-bit MCUs. You can also type the PIC16F877A. Click Next, and then let us wait for the tools to load and then select the simulator. Next, for our compiler, we will be using the MPASM or the MPLAB assembler. Next, so for the project name, we will name our project activity number 4. You can also change the project location and the project folder. So click Finish, then you will see your project directory here at the left side of the panel, and then under the source files, expand those, and then right-click New and select Empty File. So an empty file uses an arbitrary extension of the programmer's choice. For our file name, we will be naming this file as activity04.asm. So the extension ASM denotes or signifies that our program is written in assembly language. Click Finish, and then you will be greeted by the program prompt. So for our workspace, we can also type a comment header for the programmer to see what will be the function and the overall data of the program. So we can add here so you can see here on your right side there is a red line. So that acts as a margin. So it's better not to cross that line and write the comments. So we can also type activity number 4, creating an LED sequence. Program using I/O ports of microcontroller. Separated by do not forget the semicolon when you're typing comments so that the program will treat those syntax as comments. So for the first part of our program, we need to define assembler constants. Here we will define assembler constants. So assembler constant, as you may know, is the address of the specific register that we're going to use. So first is Adcon 1. We will equate it with 9FH. So 9F is a hexadecimal value. Status register will be 03H. So a lot of status register, you can also have that status register at bank 0, bank 1, bank 2, and so on. So for this program, we're going to utilize more of the registers in bank 0. So we're going to use the status register in bank 0. The price B, so we need to equate it with 0x86. So this digit 0x86 also signifies an hexadecimal value. Port B, we need to equate it with 0x06. Then try C, equate it with 0x87. Port C, equate it with 0x07. Next is the count 1 and count 2. So the count 1 and count 2 is a general purpose register. So we named it count 1 and count 2. And then we assign the value of 21 hexadecimal and 22 hexadecimal. Let's connect it. So RP0 to decimal 5, and then RP1 decimal 6. So RPO and RP1 is located at bit 5 and bit 6 of 13 register of our microcontroller. So we're going to equate it with the decimal 5. So the next part is also, this is very conventional. It is to use the OR directly to force the program to start at the set effect. Or then using. Next is to, we're going to initialize the ports. So we're going to set port B and port C as outputs. So for us to set port B and port C, let us first clear the double register to the working register. So let me just add a comment. Clears the working register. Then we need to clear bit clear status RP0 to then so this clears bit RP0 of status 6. So essentially, when you clear a bit, you're also setting the value to 0. So bit clear F status RP. Clears bit RP1 of status. So we will add additional comment here that when RPO 0 and RP1 0, therefore it selects bound 1. So let us please. So next is for us to bit clear F on the port B. So when you clear port B, you also initialize port B by clearing data latch. So when you initialize port B and clearing the value in it, you are also resetting the data latches inside of it. So we need to bank 0. Sorry. So when you clear both RP0 and RP1, it selects bank 0 because we need to access port B and clear all of the files or the bits in it. So RP0 remains 0. We now call the bit set F status 5. So the 5 we define it as RP0. You can also type RP0, but we already defined the decimal file as RP0. So bit set status of RP0 is setting the value of bit RP0 to 1. So therefore, the value of 0 on RP0 and 1 on RP0 and 0 on RP1 selects bank 1 because RP0 is 1 and RP1 is 0. So when you select bank 1, you can also access these registers. So we're going to be moving values in these registers. So first, we need to configure the pins as digital inputs. So we move 0x06, so or 06H. So this bit configures all pins, and then when we move it forward, add 1. When we move it to add 1, we configure it as digital. And then we move again 0x00 value to initialize. Then when we set 00 to the dice bit, we're defining the direction of the data. So trace B. So for us to move the value from the W register to trace B, we need this up to, and then move WF to drive C. Sets port B as outputs. Sets port C as outputs. So when we already sent the value 0 to twice bin twice C, we may now return to bank 0. So how are we going to return to bank 0? We need to clear the status of the RP0. 5 or for us to make sure, we need to also clear the value of RP. So if I come here, clears the bit RP0 and then clears the bit RP1. So we can also add additional comment since RP0 selects bank 0. We need to access bank 0 for us to write data to our bank 0 registers where in port B and port C is coming. So that selects bank 0 because RP0 is equal to 0 and RP1 is equal to bank 0. So in this part, delayed sequence program starts. So in LED sequence program, we need to have labels. So start, and then move LW. So here, we have different patterns to consider. So you can also set your own pattern, but I will set the first to AA. So AA, you may convert it to binary for you to know what is the status of bit 0 to bit 7 of the port P pins. So start, move LW 0x8, 0xAA. So we will move the value 0xAA to port P and port C. So when the program reads here, start is a label, then it moves, it sets AA value in the W register, and then moves it to port B and port C. So the logic delay starts here. So loop 1, you will use a code called deck FSC. Then you will use the count 1, deck FSC count 1, and then 1. So basically, you will decrease the value in the count 1 register by 1. So decrease, and then it will skip if the value of the count 1 register is 0. So for our comment here, we can add decreases count 1 register by 1 and skips if 0. If count 1 is 0. So if count 1 is 0, it will ask the program to jump back and then repeat the decreasing pattern again. So you will add another conditional here. Decrease deck FSC count 2. So count 2 is another register we have defined. So it's located at 22 each general purpose register. So by 1. So decreases count 2 next by 1 and skips if count 1 is equal to count 2 is equal to 0. So after executing this, it will now continue to perform another step, which is for us to light another pattern. So here we are lighting 0xAA bit. So there is a particular value to that, and then we're going to set another value for our ports B and C, so that it will light up the same different way. So move LW 0x55. Move WF port B. Move WF port C. So you can just copy here and then paste. So this time we will name the label loop. So the whole program block here, this acts as a delay. So 255 cycles for this before it moves to this one. So another 255. So all in all, we have 255 squared cycles. So this is a nested loop because it is a loop inside a loop. So you can add another pattern. So let's say you want a value of 33 for CC. Copy again this loop, which acts as a delay. So don't forget the labels here to change. So loop 2. So I almost forgot. There must be. So value of 33 is equal to 10. So we will change the label to loop 4. Then copy again. So after 33, let's say we want to light up all the LEDs, FF. So FF means we will light up all the LEDs from bit 0 to bit 7 of a particular port. So copy this one. I think this is the last two. So the speed on reading this depends on the oscillator. So usually the oscillator's value is in megahertz. So the reading of these lines is very fast. So you can notice that the program is slow at all. So here we will reiterate back to the start when all of this is done. And then you can also end. So let us check first manually. Then we will ask MPLAB XID to debug, and then see to it the problem we might encounter. So we define assembler constants. So add one is 9FH, 03H, 3C0X86. Then port B is 0X06. The 3C is 87H or 0x87. Port C is 0x07. Count 1 is 21 hexadecimal. Count 2 is 22 hexadecimal. RP0 and RP1 are decimal 5 and decimal 6 respectively. So we use the OR directive to force the program to start at the reset vector. We clear the W or the working register first before clearing the status register bits RP0 and RP1 so that we may be able to select bank 0. So after selecting bank 0, we will be access. We will now have access to port B so that we can clear port B and clear the data latches. So we now set bit 5 or RP0 to 1 so that we can select bank 1 and then move 0x06 or port B to add con 1 and then move 0x00 to initialize ISP and ISP so that the data direction will be out. And then clear with the status bits 5 and 6 so that we can be able to select bank C and then manipulate the bank C for us to access points B and C. So let us now debug the program. So in the upper toolbar, you can select debug and then debug main project. So you can see here that our program is successfully debugged. So there are no errors as seen by the microcontroller. So after debugging, we will now clean and build the main project. When you clean and build the main project, you are now going to produce the text file event for us to sign the date the program in the Proteus software. So you just need to select the directory and copy. After copying it, we now proceed to Proteus and then open the project. Select file, open project, Then you can allocate your contract for this. So activity 4 5. So let us see what is the problem. So let us start again. So as you can see, I just forgot to update button. So make sure that you click the update button for the text file to the PIC16F877A. So you can see the LED sequence pattern. So we can post it so that you may be able to assess the source. So I want to post it so that I will be able to assess. Here, in the bits port of the port F, and then it will turn off. But it is not seen because the program side is too fast. So you can just click the master key that you will reset the program. So that's all for our programming. I hope you understood what I did here. And then, if ever you have some concerns, kindly comment your concerns in our video. Thank you for watching. Thank you for patiently watching our video. Thank you.